Till now, we have looked at having a high gain amplifier present in the circuit for the readout of the capacitance. Now, we will look at a low power solution, which is more digital friendly, as well as small signal and lower technology node friendly to implement the same capacitive sensor. A quick comparison for what it should be or what it could be if we replace the inverter with a high gain amplifier. We are looking at its operation in the inverting or non-inverting mode. We would prefer the inverting mode here. So here you have the input resistance. This is your feedback resistance RF. This is the output V0. Let us apply the input value here V in. So the equation to find out what is the maximum output or what is the voltage output here is as follows. There are two conditions. The assumption is it is an ideal op amp. So when you have an ideal op amp, the conditions are the gain is infinite, and since the gain is infinite, the voltages at these two nodes, that is the input of both the amplifiers, will be same. So that is V plus is equal to V minus. It may be a zero or a non-zero quantity, but these two voltages will be the same. Next condition is there is no current flowing into the op amp. So the I input current is all zero. So what does that mean? Any current that is coming into the system will go outside of the op amp in the feedback path. Third condition that we will see is with these two conditions we will develop. So the gain is infinite is another thing that we will have to is infinite or to say infinity open loop gain. So the output V out is given as minus RF by R1 times VA. So this is the output. Now let us utilize this understanding of ours into how do we read the readout here. How do we translate the same for the inverter? So in this case, the inverter is playing the role of the ideal op amp. So it has got high gain. Right? This is expected to have a high gain. Now once this is high gain, all the other circuits are fairly simple. So the RF or the feedback resistor is given here using a capacitor in parallel with another path for the current to flow. Now let us look at the various switches and the various phases at which these switches are getting turned on or turned off. How many phases do we have? We have phi 1 and we have phi 2, right? Phi 1 and phi 2. So typical expectation is when phi 1 is on, phi 2 is off. So the waveform will look something like this. Let us look at this. So if this is phi 1, the other one will be phi 2. Assuming it is 180° out of phase and slightly off. So let us work with this assumption. So this is phi 2. Now, how many switches do we have and what are the ways are which it is operating? We have switches S0, S1, S0 bar complement, S1 complement, that is on the input side, and on the feedback side we have S2, S3 and S4. S2, S3, S4. Now what do we understand? There are two phases. So we can define this operation in two phases. When phi 1 is 0 and phi 2 is 1. So that would be this state. The other state would be when phi 1 is 1 and phi 2 is 0. Now let us look at this example when phi 1 is closed. What happens when phi 1 is closed? Phi 1 is closed here, phi 1 gets closed here, phi 1 gets closed here and here. So these are the four places where phi 1 gets closed. So what happens when phi 1 is closed? There's a short and there's a short. So whatever two things happen here. Let me mark with two different colors. We'll go with purple first for phi 1. So when there is a short, this voltage Vs is applied to the capacitor sensor. So you get Vs here. And when there is this one is short, whatever is a charge here will get discharged to 0. Right? So this is like a reset sequence is what you can do. So this CR can be reset and CX will get voltage across it. So any charge that is held can be taken care of. Next, we will see what is happening in the switches S4 and S2. So when S4 is turned off, what is all the voltage that is there at VG goes to Vout. And when S2 is turned on, all the charge that is there on CF is discharged. So this is more easily can be called as it is charge here, it is charging the capacitor sensor but discharging the CF. So it is charge CX, discharge CF. Now in the other case when phi 1 is open, so what happens? Let us give this example. I will use a different color. What happens when phi 2 is on? That is, phi 2 is closed here, and closed here. And in this case, phi 1 is turned on. So phi 1 is turned on means there is no path here. So what happens? So the capacitor sensor is discharged, and whatever is the reference capacitor, that value is pushed in. Right? So discharge CX, charge CR, that is a reference capacitor, and when this is so even the CF is charged. Charge CF. So in this case, the voltage Vg, what is coming here, will get captured. And the voltage Vg is your inverter. So these are the two stages, and in this case also it is CR is discharged. So if you see here, CF and CR work together. So that means they are doing charge amplification somewhere. And CX is opposite to their performance. So you will charge CX in one cycle, discharge CX in the other cycle. Now, where is this? This is the understanding of how the capacitor sensor works. This is a differential capacitor sensor where you are having one to detect the change and the other to nullify what is the experimental or the environmental characteristics of the sensing environment. So what will happen is, what is the value of Cx will come out, and what is the value of Cr when Cx is not present is come. So what will be your actual sensor will be delta C, which is the difference between Cx minus Cr. So this is your actual charged capacitance. Now with this understanding, we have understood the first half of the circuit. In the second half of the circuit, we need to have a high gain inverter. So in which stage of the input output characteristics of the inverter do we see a high gain. So that is when you have the input. So when input is 0, your output is high. This is the input output characteristics of a gain. So what phase or what condition do we need to operate the inverter to have a high gain? So the high gain is present when there is a high slope or linear relationship between V in and V out. So that is a very important condition. For every amplifier, you need to have a linear relationship between the input and the output. Once the linear relationship is present, it is very easy to follow. So when you operate the inverter in this particular region, that is, you should ensure that the input never goes beyond these values. So this is the range of the input that you will operate, and this is the range of the output you will have to operate. So you have to ensure that Vg is always contained within this value to ensure that your inverter performs as a high gain amplifier. So you will operate this in a high gain amplifier stage. So which is a very narrow region. So you know that this is a very narrow region. So the variation in Vg is very small. And as the variation in Vg is very small, you will come to know that the amount of capacitance change that is needed is small. So what is the activation that you need to give as an input Vs? This activation voltage for a sensor will need to be carefully controlled and calibrated. So a very narrow input change will give a very large output change. So this will also help to understand what is the value of input capacitance that you can measure. This kind of an experience with this kind of a circuit typically works in the range easily of picofarads range. So you will use a picofarad sensing area for this kind of a application.